face changing. He was very tense, and all of a sudden,
Writing's not that easy, but Grammarly can help. This sentence is grammatically correct.
Boss. Cuffs. Boss.
I've seen everything.
Damn straight. This dude is righteous.
You better stop wrapping it up.
So we start from the reminder. Next Tuesday from 15:30 for 2 hours we have the second midterm. And here's the range, then the rules. So I set it up there and you can check it out. Just a reminder for you. And then here are some writing skills that you can try to improve yourself. So I should go this way. Yeah. So we have the template for a good graph, and we have the template for good schematics and good tables, and you can print it out and take it with you to the exam. It's okay, don't worry. And here are some other writing skills, like you have to how to make your arguments complete. Maybe you can try multiple aspects, and maybe you can try to write arguments with context, which means your argument should have a reason, should have a process, and should have a conclusion. So that means that your argument is in context. So this is important. You don't need to be too anxious about the perfection of your writings. I'm sure it takes maybe a decade, maybe it takes 10 years for you to turn all of these skills into your natural acts. So if you are not perfect for the moment, it's okay. Nobody can be perfect, and you just try to practice and try to improve yourself until everything gets really natural for you. 好，那我们这边，因为上次改考卷的过程就知道说，有些同学是有很强的想要自我精进的 incentive。那这边给大家一些 hint， 科技制图就是有图，然后有示意图，然后还有表，然后我们有把这些表格的 SOP， 我们有把它上传到 New E3， 所以你可以去把它 download 下来，你就把它当成是一个 handbook 的一部分，你可以带进来考场，这个是 OK 的。然后再来是科技写作的技能，有3个，我们都会希望这3个我们都要练会啦。好，一个是你写的文章，你写的 argument， 就是你的论述的完整度。然后你能不能够用多元视角分析一个经典的问题？然后最后是你的希望你写的论述，你的 argument 是要有脉络的。那脉络的意思就是你要有原因、有过程，然后有结果、有结论。好，所以这个是脉络。那么writing skill 的部分，如果你现在没有办法瞬间就很完美，就是不要对自己设定这种不合理的目标。那个 writing skill 的部分，我们都是要不停的练习。然后以我自己的状况的话，我是从完全不会练到可以内化自然的使用，大概需要10年的时间，因为这需要经验的累积，还有你需要很多跟别人的互动，然后慢慢让你的 writing skill 变得越来越好。所以你如果没有办法一下子就写得很完整，这是很正常的，不要太担心。你就记得有这3件事情，你要一直精进就好。好 ，OK， 这是考试的部分。Then we should go on with the lectures. Today the topic is static equilibrium. Okay, and I would like to start from a documentary and from a movie. We see a little bit of clips of the movies. Usually I play the whole movie after the midterm, but this semester, because it gets shorter, we don't have enough time to do it. So we'll play another movie, but here I'm going to play a little bit of clips of this movie. This movie is called Main on Wire, and it's a story about a French artist. And he is, but this is in a very old time. It's like 1948 or 1950 sort of time like that. And he is an artist, and he is usually playing his artwork on high buildings. And he is building the wires between the building, and then he tries to walk on it. So, and then he practices a lot, and he finally is able to walk back and forth and play a little bit of trick on the wire. And here is the documentary. And then we can watch a little bit of clip of it. 这边给大家先看，我们今天从一个小小的纪录片开始。我通常是上学期我们学期还比较长的时候，我通常是会在期中考第一次期中考之后那个休息的那段时间，我会让大家看这个纪录片。对，但是因为我们今年的学期变得很短，因为我们没有时间，我们就只看短短的一小段。这个是 So this is the day when he is performing between the Twin Towers in New York. They spend 6 years to practice and to collect all the materials they need and to do the planning for the installations. And finally, this is the time when the plan comes true.
And then there was something like a relief in him. And from that time I thought, that's it. He's secure, it's good. And wow, that's...
，J'ai vu Philippe là, oui, c'était extraordinaire. C'était tellement, tellement beau. C'était comme s'il marchait sur un nuage. Et il y a eu des moments extraordinaires. Il s'est couché. Et ça, c'était l'extase de voir cette image de Philippe couché là-haut. Et puis l'autre moment très très fort, c'est quand il vous sur les traits. C'était tellement beau. Et quand il s'est agenouillé, il y a un moment où il s'est agenouillé et il a salué. Et donc je criais, regardez, les gens ont commencé à se rassembler, mais personne ne voyait. Et ils me disaient, mais qu'est-ce que vous voyez? Et je leur disais, mais un funambule, regardez, un funambule, il marche.
I sit down on a wire in one of my crossings, and I did something that amazed people. I actually look all the way down to look at something that I will never in my life see again. So I can tell you, and yes, probably it's a lie, but to me it's not. I heard the crowd. I saw the crowd. I hear them murmur.
Beyond anything you could ever imagine. It was just mind-boggling. The awe of the event and the overwhelming largeness of the scale of the situation took my mind into a place where I really wasn't that concerned about him. It was magical. It was just profound.
Observed the tightrope dancer, because you couldn't call him a walker, approximately halfway between the two towers. And upon seeing us, he started to smile and laugh.
They don't know how to react to a daydreaming wire walker laying down and dialoguing with seagull, so they were really mad.
Philippe a fait des provocations, bien sûr, puisque c'est son travail, c'est son caractère en plus. C'est-à-dire qu'il se rapprochait et les gardiens voulaient le saisir, ou les policiers, je ne me souviens plus si c'était policiers. Et là, à ce moment-là, il faisait demi-tour, donc devenait inaccessible, puisque les gardiens n'avaient pas monté sur le câble.
When he got to the building, we asked him to get off the high wire, but instead he turned around and ran back out into the middle. Everybody was spellbound in the watching of him. When we observed to the fact that he wasn't about to come in because he seemed to be enjoying it so much, we mentioned the fact to his associate, that if he did not come in, we would have a helicopter pluck him up off the wire. At which time his associate spoke to him in French, being that he's a Frenchman.
Philippe! You know? And he said, the police are going to dislodge you and you should stop. And I was madly enraged by that, but also it saved my life.
There is somebody out there in a tightrope walk between the two towers of the World Trade Center, right at the tippy top.
I personally figured I was watching something that somebody else would never see again in the world. Thought it was once in a lifetime.
Okay, but at that time, because we don't have that technology to record everything from Philippe's point of view.
Hi, I'm Dr. Amy Killen. I have my own medical practice, and I've been...
We are not able to do the record from Philippe's point of view. So there are some other movie creators, they recreated everything, what Philip see and how he maintained his balance on the wire and what are the tricks from Philip's point of view. And that movie is called The Walk. So if you are interested in it, you can grab it and you can watch it. But from my point of view, when I was watching the Hollywood-made movie, and all of these skywalking process seems very unnatural to me. From a physicist's point of view, to me that is very, very obvious that it's the computer graphic. So, but we can watch the movie and we can see everything from Philip's point of view. So let's get started. This is Philip's point of view from his autobiography. And then the movie creators just recreated everything that he ever seen.
The cops.
What the hell is that? Cuff him.
Get your hands on your head! Get down! Get down! Get your hands on your head! Down!
I'm French.
Holy shit! This one's a rock! French.
Look, fella, just, come on in. And, we'll talk about it, all right?
Okay, buddy, come on. Come on in. Yeah, show's over. Okay, come on. Parlez-vous Americano?
These officers, God bless them, they remind me of my days when I had to run from the police. But they can't follow me up here.
What the hell do we do now?
By now, I'm becoming aware of the people on the ground below watching me, my audience. And even though this is something a wire walker should never do, I look down.
And we go on with the second part. He's still on the wire between the towers.
There on my back, the sky fills my vision. The clouds, they're like music. Then something appears. An apparition. A bird. This bird is looking at me. And I feel this silent threat.
Easy, easy, easy.
Suddenly I'm invaded by doubts. I'm thinking maybe the cable is tired of supporting me. What if my towers are talking to each other? What if they've had enough? What if they decide to eject me? I'm thinking maybe it's time for me to end this trespassing.
Wire immediately. You're in violation of about 100 city ordinances. I want you off that wire immediately, or we will be forced to take steps to remove you from it.
Philippe! Philippe, ils sont fous, ils vont me tuer là! Ils veulent couper le câble! Philippe! Philippe, ils sont fous! Ils veulent te tuer! Ils vont couper le câble! Philippe! Philippe, ils sont fous! Ils vont te tuer! Ils veulent couper le câble là!
But I can't end my walk on a moment of doubt. With curved shoulders and hanging head. I decide. I will only leave my wire and my towers in victory. Officers of the New York Police Department, thank you for your patience. I announce my arrival to the police. I tell them my work is finished. Now finished. But my work is not finished. I still have 3 more steps to do.
Philippe! Qu'est-ce qui se passe? Are you okay? Easy. Whoa, 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 whoa. All right, come on.
My name is Philippe Petit. I'm a wire walker.
Hey! Come on, man. Show's over. Come on.
Don't cut the wire! Don't cut my wire!
Cut off! Nobody gives a damn about your
Too
wire!
much tension, it will snap, it will hurt someone, you have to believe me. It hallucinates with the grip voice.
He's right. Where's the handle?
It's hidden in a hole in the wall.
so this is for today. Where is it?
Good grammar and spelling.
I really recommend this movie, so if you like to and you can watch it, that's really good. But then let's come back to the physics inside. So when Philippe Petit is walking on a wire, he has to keep his perfect balance for a really, really, really long time, isn't it? So what are the key parameters that get involved in static balance? So what are the conditions for a static balance? And what is the condition for a stable, robust, and self-retained static balance? Actually, there are the same questions but answered at two different levels and two different depths. And we will go through it together. And usually if I play the whole movie and I ask the student to write down the afterthoughts, and this is a homework for them. But no, today we're not going to do it, and I'm just directly showing you the answer. 好，然后大家刚刚看完这个电影之后呢，我们再看里面的物理状况到底是怎么样。所以你想要一个静态平衡的话，有哪些关键的参数？然后呢，再来是有哪些条件必须要满足，你会得到一个静态平衡。然后呢，再接着还有另外一件事情，大家可以看到那个飞利浦，然后他在他的 wire 上面走的时候，他保持他的平衡很长一段时间内，对吧？然后很多时候我们讲说，我们有一个静态平衡，然后有一些条件要满足，可是那些条件不见得是适合那种你要很长时间的平衡的状况哦。有很多时候那只是一个暂时的，看起来很完美的平衡，但是瞬间就会破灭。所以呢，脆弱的平衡跟稳定而且持久而且有韧性的平衡，这两种平衡的差别在哪里？我们今天会讲一下这个题目，所以我们就讲到第三层深度的问题，就是你要怎么样保持一个稳定 ，robust 就是我现在忘记中文要怎么讲 ，robust 就是呢，它可以很顽固的维持在同个状态，不要改变，有点是这种感觉。然后还有 self-retained 的意思就是呢，它现在在一个平衡状态，即使等我一下。好 ，reconnected。self-retained 它的意思就是它现在是在一个平衡的状态，没有错。那你如果呢稍微去扰乱它一下，比方说像 Philip on wire， 他遇到鸟飞过来蹬他，然后有风吹。然后呢，他可能走一走脚滑，然后大家有没有看到他的脚被那个钢筋的钉子刮到流血了？然后呢，你有这些细微的扰动，但是你的系统能不能够一阵扰乱之后，它又自动自发的恢复到平衡的状态？这个叫 self-retained。所以呢，那有哪些条件满足了之后，我们可以得到一个如此稳定平衡的系统？所以这是一个看得更深入的问题。So here's a little bit of more explanation about conditions for a stable, real stable system. Stable means that it keeps the state like that, and robust means that it is very firm and it is very fixed on that state. And then the final one, self-retained, which means that if we push a little bit of disturbance or fluctuations into it, and it may leave the stable state for a little while, it may be a little bit of fluctuation, a little bit of deviations and oscillations back and forth, but anyways it decays and it goes back to the stable, static, balanced, equilibrium state. So that is called self-retained. And if you would like to achieve a system like this one, and there are some other special conditions to be fulfilled. Okay, so here this is something which is very important for our courses today. And this is the basic conditions to be fulfilled. So So if you sum all the forces up and just mind that now the force is a vector, so you have to give the strength and the directions at the same time. And when you sum the vectors up and then it gives 0, that means this is in really static balance. Okay, so the net external force on the object must equal 0. External, so mind that. This is the external one. So you can have an isolated system, but the external force on it should be, if you sum all of the forces up, and then they should be 0. And then the other one is related to rotations. So again, you have an object, and then you are analyzing the external torques on it. So torque is the force, which is the there are 2 parameters in the torque. One of them is your distance from the axis of rotations, right? And the other one is how you drive your object rotate, and that force is always perpendicular to the radius of your rotations. So that is the external torque, and that is related to the rotations of your object. And if you sum all the torques up about any axis, and it should be 0 too. So another thing is about the axis of the rotation. So this is clear and this is very intuitive. I don't think we need complicated explanations or proof on it. So this is the simplest conditions. But that is the condition for a static equilibrium, but you are not sure if that equilibrium is fragile or if it's robust. So you have to be very careful about it. 那这是静态平衡的的条件，基本的条件，这2个要满足。一个就是在外力，就是你施加在你的物体上面的外力加强等力。这个是呢，保证它不位移。好，然后再来第2个是施加在你的物体上面的力矩加强等力，这个是保证它不旋转。然后还有一个是你要注意一下，所谓的旋转呢，不管你能够找到几个旋转轴，好，针对每一个旋转轴，你的力矩都要是0。好，然后呢，这边我再多一个 additional remark， 就是这2个条件满足之后，并不保证你的 static equilibrium 是稳定的哦，就是它可能是一个暂时性的平衡，但是它非常非常的脆弱，就是你稍微碰它一下，然后这个平衡就会消失，这是有可能的。大家可以想一下，你就知道有很多状况都会变成这样子嘛。那你如果想要一个你不管怎么弄它、怎么做它，它都还是会平衡的东西，那我们还要再看得更深入一点。那么这边先做一点介绍。So here's a little bit of explanation about summation of the force. So here's an example. If you are analyzing it, or if you are working on a 2-dimensional and 3-dimensional problems, then you don't need to worry. You just need to decompose your forces and to do projections on each of the axes of your coordinate system, and then you just sum all the forces on each axis up, and then they should be 0. 那如果说你在处理的问题，你现在是在处理第1个先决条件的话呢，那假设你是在2维或是3维空间的话，你不要担心。你要做的事情就是把你的力，把它向量分解，投影到，如果2维就 x y 轴，如果3维就 x y z 3个轴。你针对每一个个别的轴向，然后让它的静力等于0，这样子就可以了。好，所以如果只是你是从1维拓展到2维、3维，那你也只是同样的动作，在2个或3个轴向上面都各做一次，这样就好了。So this is an example about the balance of the force. And here's an example for the balance of the torque. I like it very much because you can see how we model the dynamics or no, the kinematics of human bodies. 我还蛮喜欢这个例子的，因为它除了跟你示范力矩的平衡之外，你还可以看一下，就是当我们在做一些人体力学的工作的时候，你要怎么样建立模型。So this is your arm. And your arm is composed of bones and muscles. And your muscles is applying force on a bunch of bones and flesh and skins. And this is the force. So here, this is the bone, and here's another bone, and here's the connection between the bones, and this is the point where the rotation is centered. And this is your muscle, and here's the position where your muscle is pulling your upper arm. And your arm is like that, and it has a mass, it has a length, and we are going to find the center of gravity of your upper arm. So this is the center of gravity of your upper arm, and because of the weight from your mass, and here is another force which is pulling your arms to the ground. And now you are holding a book, so the book has a weight from the gravity too. And then now you can turn all these terms into a simplified model like this. So this is like the structure of your model. It's like you have a stick, and this is the position of the center of gravity of your arm, and this is for the book, this is the forces on it, and this is the axis of all of the rotations. So one of the force applied by your muscles is pulling everything up. This is the R of it, and this is the force from your muscle. And then for your upper arm itself, so this is the length, and this is the force, and you can get the torque. And this is from the book. So this is the length, this is the force, and you can get the torque. And if you can hold a book, and when the book is not falling, then you just try to calculate all of the torques, and then you just add all of them up together. And now in this problem, the question is, how much force can your muscle apply to hold everything like that? And then you can see that this is 16 centimeters, this is 38 centimeters, but your muscle is very close to the axis of rotation. It only has 4 centimeters, so you can try to rank all of the length on it. And then here are the calculations, and you can calculate it by yourself with your calculator if you want to. But this is telling you that the book is 4 kilometers. Okay, this is very heavy. But your muscle should apply 470 Newton to pull it up because of the length here. I think this is very astonishing to me. This is very, very hard for a machine to create such a big force like that. So actually everyone is a Superman, everyone is a Superwoman, your muscle is so powerful. 所以大家可以看到哦，就是你经过这样子的模型化之后，我们可以把我们的数字带进去算一算，你会发现，如果你要 hold 住一本4公斤那么重的书，你的肌肉，你的2头肌要施470牛顿的力把它 hold 住。主要的问题点是在于呢，你的肌肉离旋转的轴就支点啊很近啊，这个就4公分，其他是16跟36，因为那个比例的关系，你会发现其实每个人都很厉害耶。其实我们的肌肉它可以产生很巨大的力耶。如果你要找一个机器产生470牛顿的力，没有那么容易哦。对，你要放进去的 power 其实还蛮多的，马力啊、引擎啊，你都要蛮强的。对啊，所以大家算算之后，你就会觉得说，哇塞，其实真的是很可怕。好 ，OK， 我还蛮喜欢这个的，因为我们可以看到一个很复杂的系统，你怎么样抓住这个复杂系统的神髓，就是一些重点的部分，然后你可以把它做成一个很简单的模型，你就可以先做一些比例上的计算。好，这就是体力学的部分。Now here's another interesting topic. So if you have a lot of particles, or if you have a lot of little pieces, and you can play around like that by yourself, and how do you arrange all of the distribution of the masses, and how do you arrange the distance between them, and to make them stay balanced? So this is another problem that you have to make sure the torque of all of them should be, if you sum them up, and then the total torque should be 0. But from my point of view, usually it's faster if you do it by trial and error. You don't need to do calculations before you do this. You can just trust your instinct, and then you can just construct it by the senses in reality. 那这也是另外一个问题，就是呢，你要怎么样把你现在有一堆 particle， 或是你现在有一堆小纸片之类的东西，然后你要怎么样安排它们是怎么分布的，然后让它们能够达成一个静态的平衡。好，然后我会觉得这件事情你不如就直接开始动手做吧。对啊，因为你直接动手做，你直接当场调，然后你把你的平衡都调出来，其实我会觉得这样稍微有趣一点，还比较好玩。那你当然也可以用一些模拟啊，或者计算啊，然后去做一些你可以先做一些规划，也是可以。对，但是呢，你还不如就直接开始做，然后你就相信你的直觉，这样还不错。And then here's the trickiest one. So, we can see that the Skywalker is on the wire, and he is always carrying a stick like that. And the stick is very, very, very long and very, very, very heavy. So, why the Skywalker is on the wire? They have to play it that way. So, what is the physics inside, and how can we explain it? So now we are trying to go through some important details in it. Here's a little introduction about center of gravity, but I think this is not very difficult because it's just exactly the same concept like center of mass, but the only thing is that now the CG, the position of your center of gravity, is weighted by the force caused by the gravity. So that's the only difference. But the concept is exactly the same. And now we are living in a world where the gravitational acceleration is just the same. So usually the center of gravity is just equal to the center of mass. So this is not very complicated, and you can just do it. If you somehow live in a magic star where the gravitational force is varying in space, and then we have to be really careful. 那在一般的状况底下，因为我们现在住的地方，我们的重力场是均匀的，所以通常直心跟重心两个是一样。对，那假设说你有一天你当了太空人，你去一个神秘的星球，然后它的重力场会随着位置改变。啊，如果是那种状况的话，那你就要小心一点，你要再重新做过计算。好 ，OK, center of gravity. Okay, then I think we go on. 我今天上课的话，我都会一直往下上，我们中间就不休息，因为我刚刚看你电影嘛，应该没有很累。那如果你想要上厕所，你就出去，好，你就静静的出去，静静的回来，我们就一直往下，因为我们现在看影片很多，我们就慢慢往下看。Okay, so this is how you can find the center of mass and center of gravity just by experiment. 所以这是一个影片，告诉你说你要怎么样做实验。用做实验的方法，你就直接手动，然后就找到 center of mass and gravity， 然后你不需要透过电脑软体。In my courses of the physics lab in the second semester, I usually ask the students to take whatever they want to measure, hang it somewhere, and measure to characterize the simple harmonic oscillation of that whatever thing. So they can take something like a clothes hanger, they can take something like every kind of shape, and then suddenly they ran into the problem that where is my center of gravity, and then they can spin around for a really long time. But actually this is not very difficult and you can watch it. 通常啊，我的跑步实验到下学期的时候，我会请学生就随便带一个他最喜欢的东西来实验室，上面要有个洞，然后就请他把那个东西就挂在一个架子上面，然后让那个东西去做简谐震荡，然后他要自己想办法去分析那个简谐震荡的基本的一些性质，比方说自然频率啦，比方说自然频率嘛，然后自然频率就会跟重力，然后还有它的重心跟支点之间的距离等等。然后一讲到要找重心，大家就傻住了。就是比方说，如果那个学生他今天有点懒，他就直接从宿舍的衣架上面就拿一个衣架来，我就挂在那边这样子转。然后可是衣架的形状完全没有对称性啊。那这个时候你要怎么找你的重心？在实验室里面又没有 simulation 的软体，然后呢，你要怎么办？对，然后其实很简单。
In this demonstration, we're going to see how to find the center of mass of an irregularly shaped object. For the object, we're going to use the state of North Carolina. In order to help with this, I'll be using this piece of equipment. There's a nut tied to a string with a pin tied on the end. What I'll be doing is using this string with this pin and a weight attached to it, together with the map, so that I can suspend the map from the pin and see where the string falls. So I'll begin by putting the pin here. This can be anywhere, but I'm just picking somewhere around Elizabeth City. I hold the end of the pin so that the map is suspended from my hand. So this means that the center of mass of the map will be somewhere along this vertical line. With a marker, I'll draw the line on there. It's kind of a rough line, but you get the idea. So we know the center of mass falls somewhere on that line, but we don't know where. In order to find out, we need to draw a second line to intersect with the first. So to do that, I'll put the pin in somewhere else, somewhere up here around Boone. Suspend it once more. Draw another line. And that's enough to find the center of mass, which should be the intersection of those two. But just for good measure, we'll do it one more time to see if the third line also passes through that point. So I'll put this somewhere down around Wilmington. And I don't have to draw the line for you to see that the string is passing very near that intersection point. So no matter where I put that pin, it should pass through that particular point. And let's see where that is. It turns out that it's very close to the city of Sanford. So if that really is the center of mass of North Carolina, then I should be able to balance the entire state on that particular point. Now, when I said that Sanford was the center of mass of the state of North Carolina, I was talking about this cutout of the state. Actually, the center of mass is influenced by the distribution of mass in the object. And for North Carolina, we know we have mountains to the west, and so that's going to increase the mass on the western end. And we have bodies of water distributed throughout the state in various places. So all of these will affect the actual center of mass of the state of North Carolina.
Yeah, this is how you can do it. This is how you do vector analysis and just linearity. 所以呢，我们有时候就用那个数学这样子算很多东西，然后你在现实中你要怎么操作呢？其实就是像刚才这位老师示范的一样，它其实没有你想象那么复杂。好，我想要先把它缩小。OK， 好，然后呢，等我一下。好。And then here is another tricky one. another important trick to get a static balance. So you can see that when he finds the center of mass and when he places that big pieces of the map on a needle, and that is really unstable, isn't it? He has to constantly, slightly push or support the cardboard and to let it stay on a static state. And then here is another video about how you keep the balance for a very long time without spending effort on maintaining it.
We're going to be looking at several demonstrations that have to do with center of mass and how the position of the center of mass of an object is related to the object's stability. Let's begin with a parlor trick that you've probably seen before. Take a fork and a spoon, interlock them, slip a match in between the tines of the fork and balance it on a glass, or in this case a beaker. And you can make the whole combination balance there. The reason that works is because the center of mass of the system of the fork and the spoon is actually right at the lip of the beaker where it's balanced. So the point of support is directly below the center of mass. The reason the center of mass is at that particular point, it's not actually within the fork or the spoon, it's somewhere here below it. Now, by symmetry, since the fork and the spoon are about the same shape, the center of mass is going to be along a line approximately here. But because the spoon extends way out and the fork extends way out, this will displace the center of mass downward. And so the center of mass of an object does not actually have to be physically within the object. Let's look at another example. Here we'll be using our two-dimensional NCSSM student. We'll call this 2D. And I'm going to put some weight on 2D's hands and balance 2D right there on the top of the head. It's very easy to balance. Now, like the fork and the spoon, we've got a lot of weight on the outside, extending out away from the point of support. Because of the symmetry of the object, the center, we know the center of mass will fall on a vertical line right here, below my finger. And it's going to be quite a ways down because most of the weight is here on the clamps. Now this is a very stable object. So next we want to talk about why it is that this is stable and what the position of the center of mass has to do with that. I'll begin by looking at a different object where it might be a little bit easier to see what's going on. I'll just use this. This is a support for another piece of equipment. It has a wooden base and just a metal rod. Sitting like this, it's very stable. It's very hard to make this thing tip over. But if I put it like this, it's essentially impossible to keep it from tipping over. That has to do with what happens to the center of mass when the object tips. The center of mass of this object is inside the piece of wood. In order to tip the object, notice that the center of mass has to rise first. It's going to rise before it finally starts to fall over again. It has to rise quite a large distance. On the other hand, if the object is like this, the center of mass is now up here, and as the object starts to tip, the center of mass immediately begins going downward. So the difference is that if the center of mass has to be lifted, then the object is going to be more stable than if it just falls immediately. And the farther it has to be lifted, then the more stable the object will be. Now let's take a look at 2D one more time. The center of mass of 2D is way down here because that's where most of the weight is. So I would actually have to pull this to the side like so in order to raise the center of mass. And in fact, I couldn't even raise the center of mass far enough in order to make the object tip over completely. On the other hand, if I put most of the mass above like this, now the center of mass of 2D will be up here, it will be above my finger. So as soon as I let go, the center of mass will fall immediately. And it would be impossible for me to balance without moving my finger. And even then, it's very difficult. Now, there are a number of toys that work on this principle. Here's one of them. This horseman has, the horseman is plastic, and there's a fairly heavy weight here on the end. So the center of mass is going to be down in here. Actually, the center of mass might be somewhere within the weight here on the end, or at least very near to it. We have no trouble balancing this on its platform. The center of mass is way down here below it. In order to make this thing tip over, we'd have to raise the center of mass above this point, and of course, that would be impossible without practically pushing it off of its stand. Here's another toy that works similarly. It's a bald-headed eagle, and this one can be balanced on its beak. Now, if you want to try this yourself and don't have toys like this at home, it's very simple. All you need is a pencil with an eraser and a paper clip. Open up the paper clip. Stick one end in the pencil eraser, and you can balance the other end on your finger. So the center of mass will fall on a straight line directly below my finger.
你现在就可以开始到处吓人了，对吧？你就可以弄一些这些奇奇怪怪的小东西，可以描述给人家看。Okay, so he is explaining it in a way that by comparing the position of the pivot.
口罩侦测，确保每位职业驾驶上线前都戴上口罩。Uber。
And I think his explanation is a little bit too simplified. And since we already learned the concept of energies, and we can explain it in the energy point of view. 然后刚刚这位老师他解释，他做了很多 demonstration， 然后他的解释比较直白，就是你会看到说，他想要判断一个东西的平衡是不是稳定的，判断的重点是比较支点跟重心的高度。如果你的重心是在支点的直线的正下方，那通常你的系统就会是稳定的。那即使说它的形状看起来非常的 tricky， 它的形状看起来非常的不规则、不确定，或者是看起来非常的纤细、非常的千奇百怪，但是只要你能够把你的重心放在支点的下方，你基本上就可以维持一个非常稳定，然后 self-retained 的 equilibrium 的系统。但是这样子的解释，以我们的程度来讲呢，有一点太直白了。我们已经学过能量的概念，我们学过重力位能，我们学过动能的概念，所以我们现在要从能量的观点来重新诠释一次他刚刚到底做了什么事情。So, what is the dynamic point of view for a static, balanced equilibrium system? So the thing is, if you, where is my mouse? So now the question about the positioning of your pivot and your center of gravity. So in this case, the center of gravity is the axis of your symmetry, and this is the position of your center of gravity, and this is your pivotal rotations. And when your center of gravity is here, and then you can have a stable system. But if you put your center of gravity up, if you push it up, and I should say the mass here, and because it's in a gravitational force field, and then now you are putting a lot of potential energy, gravitational potential energy into these heavy clips, and to release that potential energy, which is U is equal to mass, and G is the gravitational acceleration, and H is the height. To release that energy, it's better if it flip over, and if all of these heavy things just get back to the position, which is lower than your pivot. And if you somehow created a installation like this, if you somehow accidentally put the center of gravity higher than your rotational axis, and then the system can be highly unstable. And because your potential energy needs to be released to reach to a equilibrium state. So that is the point in it. 然后你用比较动力学的观点去诠释这件事情，就是呢，假设你在把你的系统搭起来的时候，你刚刚好的把一大坨很沉重的东西都堆在上面，就是在你的旋转的支点的上面。那这个时候，它们就会累积出一大团重力位能。我们现在在重力场里面嘛，因为我们活在重力场里面。那为了要把那一大团重力位能释放掉，那你的那一堆质量很沉重的东西，它们就会翻下来，翻到你的支点的下方，它可以达到一个重力位能更低的状态。所以呢，这就是为什么呢？这个就是所谓的 unstable 跟 stable 的差别，就是你的位能在你整个系统里面，你的位能到底是不是在最低点？好，那这个是在重力场里面的事情嘛。然后我们还有弹性位能，然后还有一些别的位能。对，那么我们几乎在所有的物理学的系统里面都是这样子，就是只有当你把你的整个系统调到的状态是位能最低的时候，然后它才能够达到一个平衡，而且它可以自己自动自发保持平衡的状态。So, and this concept applies to, I think, it applies to most of the physical systems. Every kind of potential energy, and now this is the gravitational potential energy, and sometimes we have the elastic potential energy, and we have the chemical potential energy, and other kinds of potential energy. But in every kind of system, and you can always try to rearrange your things. You try to reach to the minimum potential energy, and that is exactly the state where you can be very stable, and that stability is self-retained. So this is a very important concept. And finally, when we are constructing an experimental setup, when we are constructing a physical model, and we need to run through this process to find the equilibrium first, then we can go on with other complicated analysis. 好 ，OK， 那我们其实你就会发现，其实物理学家就会开始，就会用同一个想法开始去复制很多成功经验。就是我们每次只要一有一个新的物理学的模型或是一个新的状况，我们第一件事情一定是想办法找到位能的最低点。就是我的物体要怎么安排，或者是我的系统要怎么架设，怎么架起来，然后它的位能是会在一个最低的状态。位能的最低点找到之后呢，你再去做 perturbation。就你再去做一些扰乱，然后你去观察，那我扰乱它之后会发生什么事情 ？And if you're working in a multidimensional system, if you have multiple parameters, if you have multiple potential energies, and then the problem get really complicated because sometimes you have many minimums. You have different minimums distributed in the potential field, and sometimes the minimums are. Sometimes you have a minimum here, but just not far away, you have another minimum here. And they can distribute it in a multidimensional space. So if you have a lot of minimums, and then it could be problems with excitations, and when you excite the system and when it gets really energetic. But sometimes when all of these energy is starting to be released, and you need to be able to predict where is the landing point for the minimum potential energy. And if you have a lot of minimums, then it can be a big problem. So that is the point when you are really working with real physics. 那很多时候，如果你一个系统里面你有很多种位能的话，事情就会开始变得有点麻烦。对，因为我们这边是我们只有看重力位能，你会觉得很简单。但有的时候呢，你会有重力位能、电磁位能、弹性位能、化学位能，对，很多它会全部都搅在一起，然后那你就要开始去做那种多维度的 的模拟咯，你就要去找一下，哇，那我这么多位的排列组合起来，它的最低点在哪里啊？然后那个最低点还不见得都在同一个高度哦，就是它有的可能最低点在这里，另外的排列组合的低点在这里，另外的排列组合的低点在这里。那有时候它的所谓的低点也不是一个谷底，有的时候是你在某一个轴向上面是这样，但是另外的轴向上是这样，然后那个点它也会出现一些奇妙的行为。那这个时候呢，如果你把一些能量放到你的系统里面去，其实在物理上我们会叫它你做 excitation， 就是你让你的整个系统变得非常 energetic， 非常活络，然后它可能就是混乱一阵子，然后很高能状态一阵子之后，这些能量会全部用别的方式会散出来，就散溢出来。那当你的这些，比如说 particles 或是一些物体，它要从高能量状态回到低能量状态的时候，它的落点在哪里啊？那假设说你的 potential minimum 很多的话，你头就大了，对，因为你就变成，在实际上你看到的状况就会是呢，你做一个实验，每一次结果都不一样，这就会是你看到的状况。好，那我相信大家在以后，比方说，如果你是在产业界里面当工程师，尤其是你是做制造的东西的时候，制造你要同时处理很多个参数，你就会一直反反复复的遇到这种问题。对，就是你参数这么多排列组合，我要怎么样去弄出一个不管我的参数怎么变化，都一定是能量最低点，这样子你才能够保证，比方说你做出来的晶片100万片，全部它的 quality 都是一样的，你不会变成说100万片，然后会有100种不同的形态。对，那么在制造上面就会是很重要的，就会是很严重的问题。OK， 好，所以大家可以记得这个观念，因为这个观念以后会一直出现，它会变成我们很多物理学的模型要开始分析的第一步。那这个影片就有兴趣的再自己看，它其实是在讲同一件事情，只是他又做了一个更厉害的实验。So if you're interested, then you can watch it again. This is balancing 2 glasses of water on a plate and with a high long support. But basically it's telling you the same thing. It's how to arrange your pivot and how to arrange your center of gravity and how to reach to a minimum potential energy. And let's come back to Philip. And so what is the things that he's done right to keep himself in balance for such a long time? 所以这 Philip 到底做对了什么事情？所以他可以在半空中站在一个钢丝上面，他可以保持他的平衡这么长一段时间。So let's look at the geometry of Philip plus his sticks. 所以我们现在看一下这东西的几何结构，就是菲利普本人跟他的那根平衡杆。So you can see that actually most of the problem when he is walking is the flip over. And when you're flipping over, then actually it's a problem with rotations. So if you have a very long stick, and you can see the arms are very, very long. The arms are very long, and if you remember the equation for moment of inertia. So if you have a very long arm and you have a big moment of inertia, so the contribution from the long stick is the large moment of inertia. And when you look at the documentary and when you look at the movie, you can see that the stick is very large and very heavy. So for the contribution of moment of inertia, the mass is getting very big too. And if you have a very large moment of inertia for rotation, which means that you have to put in a lot of force to make it rotate. And if the force is not large enough, and it moves in a very slow way, and that is the point. So even if when Philip is holding a long stick, long heavy stick like that, and when he is walking, and even if he is a little bit out of control, and even if he has a little bit of deviation from the equilibrium point, because the rotation of him is so slow, so he get more time for himself to get back to the equilibrium position. So this is the point. And when you have a big moment of inertia, the speed of rotation is very small, so he has the time to modulate himself to maintain the balance. So that is the secret behind the Skywalkers. 好，所以大家可以看到说，他为什么要抓一根这么长而且这么重的棒子啊？那主要的原因就是，你如果可以创造出一个这样子的几何形状跟这样子的质量分布，你可以创造一个非常巨大的转动惯量。那菲利普他就是同一个人，他如果小小的歪一边，或是他出力的时候有一点小小的不平衡，那是没有关系的，因为他出的力很小，他转动惯量又这么大，所以其实它能够造成那个 flip over 转动的速度其实是很小，就很慢啦。那所以他在这样子的状况底下，他可以帮自己争取更多时间去调整他的身体姿势，或是去调整他的两只手背的出力等等，然后去把他自己调回一个平衡的状态。所以这个是为什么他只要习惯了那样子反复 modulate himself 的过程呢，他就可以一直保持平衡。他甚至可以像这样子，就躺在他的 wire 上面睡觉。就他累了，他可以小睡一下，他可以睡醒以后再继续往前走。OK， 所以这是还有一个点。And here's one more remark. If you look at the shape of the stick, you can see that it's a little bit higher at the center, and the two ends are slightly down, so it's a little bit curved. And that design makes your center of gravity lower than your axis of the flip over. So that is another design to keep the static balance. 那还有另外一个点是，你如果观察一下，在这里这张图上不明显，但是呢，你如果刚刚在那个 documentary 里面你有仔细看的话，你会发现它的那根平衡棒其实不是直的，就是它中间是凸起来，两边是凹下去。那它的 center of gravity 就会在它翻过来的时候，它翻过来的时候，它一定是会有个轴心嘛。那它的 center of gravity 就会在那个轴心的下面正下方。如果它可以保持自己对称的话，就会在它的支点的下方。所以这也是另外一个小 trick。它是因为这样子，所以可以保持自己在一种很长时间平衡的状态。Okay. So this is the secret behind the wire walkers. Okay, so here is a summary for how to stay balanced, and this is the stable balance, but not the temporary balance. This is the stable balance. So the pivot must be higher than the center of gravity, and if you can create a large moment of inertia, then you can slow the rotation down, and you can have more time to regulate yourself. Therefore, the answers of the three questions that we started. The answer for the let's do it this way. So here are three questions. The key parameters that involved in static balance. So key parameters. One of them is all the key parameters for linear motions. And the other key parameters are for rotations. So basically, you are combining the two kinds of the linear motions and the rotations. You have to consider all of them together. And the conditions for a static balance is this one. So the sum of the force and the sum of the torque, and the conditions for a stable, robust, and self-retained. So the key parameters involved in static balance. One of them, you can see the force, the torque, and then if you need to keep it stable, you have to consider the moment of inertia too. And here are other key parameters like position of the pivot and the center of gravity and how you align them on a straight line and how to keep the symmetry. So there are a lot of key pointers actually. You can try to think about it and you can try to summarize it by yourself. And conditions for static balance is the simple one. This one. So if you fulfill the two conditions, then you have a static balance. But it doesn't mean that the static balance is stable. And if you want to keep it stable, robust, and self-retained, then this one. You have to think about it a little bit. It's this one. So this is the balance in a long time stable equilibrium. Okay, so this is all for today, and I just put the announcement for the second midterm here on the screen, so you can check it out if you need to. And our lecture is just up to here, and good luck for your exams next week. 那我们今天上课就先上到这边。我等一下会把期中考2的内容和规则我放在这边，有需要的同学就自己再看一次。好，那就祝大家下周考试顺利。
学更好。